Welcome to another video on linear algebra. So today we're going to be going over special matrices. Now the first special matrix we're going to be going over is the diagonal matrix. Now the diagonal matrix you'll be seeing a lot. So in this matrix we have d sub 1, 0, 0, d sub 2. Now d sub 1 will have a condition as well as d sub 2 where they cannot equal 0, because then you just have the 0 vector or 0 matrix. But that's not what we have here. We also have another one where it also looks like a diagonal matrix. And this is going to have an exponent of n. Well, if this matrix has an exponent of n, we are just going to put the exponent on the values. Oops. Just like that. Okay, and we also have d sub 1. So let's just say A, B, and C. Okay, so we also have d sub 1, 0, 0, d sub 2 to the negative 1 power. Well, that's just going to be inverting the d sub 1 and 2. So you're going to have 1 over d sub 1, 0, 0, 1 over d sub 2. And those are the special triangles for, special matrices for a diagonal matrix. So if you want to see a couple of problems, we can do a couple. So this one says to find a squared, a to the negative 2 power, and a to the negative k, where k is an integer, by inspection. So basically they want you to look at it, be an inspector. Here's your A matrix. So if I were to square the A matrix, I would have a 1, 0, 0, and a 4 if you were to square it. If you can see that, a squared is equal to 1, 0, 0, 4. That's how you do it. And if you wanted the a to the negative 2 power, that's just going to give you 1, 0, 0, 1/4. Okay, and a to the negative k, you have 1 over 1k, and then you have 0, 0, 1 over negative 2k. Oh, you want to put brackets on there. If you want to put parentheses, you could say determinant and then put parentheses. But that is the diagonal matrix. Super special. So let's talk about another one called the triangular matrix. So super simple. The triangular matrix is exactly what it says in the name. You're going to have basically some numbers over here, and you have zeros here. Or it can be the other way, where you have numbers here, and then you have zeros there. So that's what it could look like. Nothing too special, but it does have the special name. So the next one, pretty special. You have the symmetric matrix, where A is an n by n matrix, and A is symmetric if and only if A is equal to A transpose. So A in the form of diagonal or triangular matrix, and the theorem is A is invertible if and only if the main diagonal does not equal 0. So what does that mean? What that basically means is, let's go ahead and take a look at a problem. So we have negative 1, 2, 4, 0, 3, 0, 0, 0, 5. Okay. So if I were to look at this matrix, I can already see that I have a diagonal matrix. And if I were to add these up, plus 5, well, that's going to equal something that's not equal to 0. So, yes, this would be invertible. Invertible. Okay. If it was 0, then it would not be invertible, right? Another cool problem is if we were asked to find all values of x for which A is invertible, and they gave me an A matrix of x minus 1/2, 0, 0, x minus 1/3, 0, x squared, x cubed, x plus 1/4. So if they're asking me to find all the values for x which A is invertible, remember, we want to make sure that it's not 0 so that it's invertible. So we want to, I guess we could prove by, we can show that something is invertible by showing that it's not invertible, right? So we can say that x cannot equal 1/2 or 1/3 or negative 1/4. Why? Because if you see, if I were to plug in x here, it was 1/2, that would be 0, right? And if I were to plug in 1/3 here, that would be 0. If I plug in a negative 1/4 here, that would be 0. And if I were to add up this diagonally, that would be 0, and that would not be invertible, right? Because if it's 0, it's not invertible. And if it's not 0, it's invertible. So that's basically the special matrices. And we'll be going over transformations in 1.8. So in the next video, it's going to be the real stuff. So thanks for watching. Hopefully this helped.